Now question number 15. The question is, derive an expression for the effective resistance for three resistors when they are connected in number 1 series, number 2 in parallel. Now the first one, series combination of resistors. The definition is, two or more resistors are said to be in series if same current passes through each resistor when some potential difference is applied across the arrangement. Let me explain. Let us consider three resistors which are connected end to end. Each resistance here taken as R1, R2, R3 like that. And this arrangement is connected across a battery. A battery of EMF V. So in series combination, what happens? Current through each resistance must be same, because for the flow of current here only one path is available. That's why current through each resistance must be same. Now using Ohm's law, we can write here potential drop across each resistance can be written V1 is equals to I R1, because in series combination applied potential is divided across each resistor. Therefore, using Ohm's law, V1 is equals to I R1, V2 is equals to I R2 and V3 is equals to I R3. But total applied potential V is equals to sum of the individual potential differences. That is, V is equals to V1 plus V2 plus V3. Now V is equals to V1 means IR1, V2 means IR2, V3 means IR3. In all these terms, I is common. Let us take it as common. I into R1 plus R2 plus R3. Take this as to be equation number 1. If Rs is the effective resistance of the series combination, then V is equals to I into Rs. Equation number 2. Now 1 and 2 are equal. Equate them. That is, IRS is equals to I into R1 plus R2 plus R3. IRS is equals to I into R1 plus R2 plus R3. So I gets cancelled. Therefore, RS is equals to R1 plus R2 plus R3. So this is the effective resistance in the series combination. Means the effective resistance of a series combination is equals to sum of the individual resistances of the resistors. This is about series combination of resistors. Now second, parallel combination of the resistors. What is the meaning of parallel combination of resistors? Two or more resistors said to be in parallel if potential difference across each resistor is same when some potential difference is applied across the arrangement. Let me explain. Let us consider three resistors whose resistances taken as R1, R2, R3. Now the common ends are connected together at two different common points, and this arrangement is connected across the opposite terminals of a battery of EMF V. Now what happens? Current which is coming out from the battery here divides into three parts because it has three ways. Then total current I can be written as I1 plus I2 plus I3, equation 1. But potential difference across each resistor must be same. Then only the combination is known as parallel combination of resistors. But by using Ohm's law, I is equals to V by R. So I1 can be written as V by R1, I2 can be written as V by R2, and I3 can be written as V by R3. Therefore, the above equation can be written as I is equals to V common in all terms. Take it as a common, 1 by R1 plus 1 by R2 plus 1 by R3. Okay, but RP is the effective resistance in parallel combination of resistors. Therefore, I can be taken as V by Rp. Then we can write these two equations as V by, if you take this has to be equation number 2 and this has to be equation number 3. Now 2 and 3 are equal, then equate them. It becomes now V by Rp is equals to V into 1 by R1 plus 1 by R2 plus 1 by R3. So here we cancel out, and final expression is 1 by Rp is equals to 1 by R1 plus 1 by R2 plus 1 by R3. So what is the meaning of this equation? The reciprocal of effective resistance in parallel combination is equal to sum of the reciprocal of resistance of the individual resistors. So this is the formula for parallel combination of resistors. Now the question number 16. The question is, how do you distinguish dia, para and ferromagnetisms in matter? That is nothing but comparison of dia, para, ferromagnetic materials. Let me explain. First point, in the case of diamagnetic materials, the substances which have tendency to move from strong magnetic field to weak magnetic field are generally named as diamagnetic materials. Means having tendency to move from strong magnetic field to weak magnetic field. So such type of materials are generally called as diamagnetic materials. In the case of para, the substances having tendency to move from weak magnetic field to strong magnetic field. So having tendency to move from, Here it is strong. In this case, weak magnetic field to strong magnetic field. So the difference is very important. In the case of diamagnetic material, the materials having a tendency to move from strong to weak. But in this case, these having a tendency to move from weak to strong. That is very important. In the case of ferro, the substances having tendency to move from strongest tendency, to say exactly strongest tendency, the substances having strongest tendency to move from weak magnetic field to strong magnetic field. Almost this point is same, but strongest tendency to move from weak magnetic field to strong magnetic field. So these type of materials are generally known as ferromagnetic materials. This is about the first difference. Coming for the second, in the case of dia, these materials are repelled by the magnet. So repelled by the magnet. Now paramagnetic materials are feebly attracted by the magnet. Now in the case of ferro, these are strongly attracted by the magnets. Strongly attracted by the magnet. This is about second point. Coming for third point, these are weakly magnetized which are placed in an external magnetic field. So weakly magnetized in a direction opposite to the external magnetic field. So the important point is, these materials are weakly magnetized in a direction opposite to the applied external magnetic field. In the case of para, these are weakly magnetized in a direction parallel to the magnetic field. So weakly magnetized in a direction or in the direction of the field, in the direction of the magnetic field. Now in the case of ferro, these are strongly magnetized in the direction of the magnetic field. This is the third point. So the important point is, these materials are magnetized in a direction opposite to the applied external field, magnetic field, and paramagnetic material are weakly magnetized in the direction, means parallel to the applied magnetic field. In the case of ferro, these are strongly magnetized in the direction of applied external magnetic field, means parallel to the field. So these are weakly magnetized and these are strongly magnetized in the direction of applied external magnetic field. Fourth point, in the case of dia, when a diamagnetic material is suspended in a uniform external magnetic field, they come into rest in a perpendicular direction to the applied external magnetic field. That means, suppose if you take a marker, is a best example for a diamagnetic material. If you suspend this material like this with the help of a torsionless thread in the presence of external magnetic field, suppose this is the direction of external magnetic field, this always comes into rest perpendicular to the direction of applied magnetic field. So that means in this case these materials are coming to rest perpendicular to the field, external field. Now in the case of para, these materials, if a paramagnetic material is suspended in a uniform magnetic field, these materials comes to parallel to the applied external field. So coming to rest parallel to the external field. Now in the case of ferromagnetic materials suspended in a uniform magnetic field, then they come to rest parallel to the field, and strongly they are coming to rest parallel to the field strongly only. That means almost para and ferro having same property in this case. So these are also coming to rest parallel to the external magnetic field. Fifth point, intensity of magnetization. Generally it is represented by symbol I. Intensity of magnetization for diamagnetic material value is low and it is negative. Intensity of magnetization for diamagnetic material is low and is negative. In the case of para, it is low but positive, and for ferro I is high and positive. That's a major difference. Number 6. Now susceptibility, magnetic susceptibility, symbol chi is low. Susceptibility, magnetic susceptibility chi value is low and it is negative. Similarly, for and paramagnetic material, chi is low but positive, and for ferro, magnetic susceptibility value is high and positive. Number 7, mu r. What is mu r? Generally mu r is known as the relative permittivity. So mu r value for diamagnetic material is less than 1, for para greater than 1, for ferro much greater than 1. The last point, examples. For diamagnetic material, examples are silver, bismuth, copper, H2O, etc. In the case of paramagnetic material, examples are aluminum, manganese, platinum, oxygen, etc. Now, ferromagnetic material. Examples are iron, nickel, steel, etc. These are the examples for different magnetic materials. Like this, we have to explain the comparison of dia, para. Now the question number 17. The question is, explain distance of closed approach and impact parameter. Let me explain. Distance of closed approach or size of nucleus. According to Rutherford's alpha scattering experiment, we can estimate the size of a given target nucleus. For example, let us consider this has to be nucleus of a target. We know that a nucleus having positive charge. I am considering charge of the nucleus as Q is equals to plus ZE. Now, from the large distance, an alpha particle is moving with some velocity v alpha, where m is the mass of alpha particle. This is alpha particle. From large distance along the center of the nucleus is also called central line. So along the central line, from far point, an alpha particle is moving towards the nucleus of given nucleus. So here alpha particle having some kinetic energy, that is Ke is equals to half mv alpha square. Say charge of the alpha particle, here it is taken as 2e. I am taking Q1 is equals to 2e, whereas charge of nucleus is Q2 is equals to plus Ze. Both are the positive charges. Now, positively charged alpha particle is approaching towards the center of a nucleus with some kinetic energy. As it is approaching towards the nucleus, then alpha particle experience repulsion force. So what happens? As it is approaching towards the nucleus, its kinetic energy gradually decreases, and in turn it converts into potential energy between the nucleus and alpha particle system. Say at a particular distance, suppose alpha particle is approaching like this, at a particular distance from the center of the nucleus. Say I am taking this has to be a particular distance or not. When alpha particle approaches to this point where entire kinetic energy of alpha particle converts into potential energy between the alpha particle and the nucleus. That means at this particular point, the alpha particle comes to rest for a moment and immediately it retraces its path back through scattering angle 180 degree. Then this distance, the distance at which total kinetic energy of alpha particle is converted into potential energy between the nucleus and alpha particle is called distance of closest approach. That explains about the size of the nucleus. So now mathematical form. at r naught distance from the center of the nucleus, kinetic energy of alpha particle, total kinetic energy of alpha particle is equals to potential energy, to say exactly electrostatic potential energy between alpha particle and the nucleus. So this is a mathematical form. It is possible at this distance only. Now Ke alpha is equals to potential electrostatic potential energy formula 1 by 4 pi epsilon naught q1 q2 by r is the general formula. But here Ke alpha is equals to 1 by 4 pi epsilon naught q1 means charge of an alpha particle, that is 2e. Along with signs we have to take, but here both the charges are positives, therefore no problem to write the signs, and q2 is nothing but ze and distance is nothing but r naught. Therefore r naught is equals to means size of the nucleus, that is also nothing called as distance of closest approach, symbol is r naught. So r naught is equals to 1 by 4 pi epsilon naught 2 ze square by kinetic energy of alpha. So this is the expression for size of the nucleus, where K alpha is nothing but half mv alpha square. M is mass of the alpha particle and v alpha is velocity of the alpha particle. So this is about distance of closest approach. Now second one, that is impact parameter. It is represented by symbol small b. First of all, definition. The perpendicular distance of the velocity vector of the alpha particle from the center of the nucleus when it is far away from the nucleus is called impact parameter. Now let me explain about it. Let us consider this has to be nucleus of a target atom. This is the nucleus of a target atom or target nucleus. Now we know that this has to be considered as central line. Say from far point an alpha particle is approaching towards the nucleus with some velocity, that is v alpha. We know that alpha particle having positive charge, nucleus having positive charge, then alpha particle when it is approaches towards the nucleus then experience repulsion force. So what happened? Then it deviates from its path, then it becomes like this. So as the alpha particle is approaching towards the nucleus, due to repulsion force, it gets scattered through certain angle, that is, here it is taken as theta, where theta is called angle of scattering. Angle of scattering. Now, the perpendicular distance of the velocity vector, here it is called velocity vector of the alpha particle, from the center of the nucleus when the alpha particle is far away from the nucleus. That is called impact parameter. So, mathematical form for the impact parameter is given by B is equals to 1 by 4 pi epsilon naught Z E square cot theta by 2 by Ke alpha, where Ke alpha is what? Ke alpha is nothing but kinetic energy of alpha particle. M is mass of the alpha particle, V alpha is the velocity of the alpha particle. Now from this, in the case of head-on collision, if B means impact parameter is very less, then scattering angle becomes more. The maximum possible value for scattering angle is almost equals to 180 degree. That means if B is very less means B is 0. If B is 0, then alpha particle travels along the central line towards the nucleus of a given target, then angle of scattering value becomes 180 degree, means it retraces its path. That's the one condition. Now condition 2, if B is more, then scattering angle almost becomes to 0 degree. That means as impact parameter values are changing, scattering angle also changes. This is about explanation of impact parameter. Now question number 18. The question is, what is rectification? Explain the working of half wave rectifier. Let me explain. First of all, rectification. The process of converting alternating current or voltage into direct current or voltage is called rectification. Means is a process by which alternating current can be converted into direct current, and for which a device is used is called rectifier. Now we have to explain about working of half wave rectifier. Working of half wave rectifier. Half wave rectifier. So generally half wave rectifier is constructed by using a diode, PN junction diode, with the help of a transformer, transformer having two coils, primary and secondary coil. The two terminals of primary coil are connected to an AC source. This is the AC source, alternating current source, which acts as input AC source. Now to the secondary coil we have to connect a diode D, and a load resistance is connected across secondary coil by using diode. So RL is the load resistance which acts as output resistance, then output is taken across the load only. So this is the construction of half wave rectifier. Now it's working. So I am taking this as to be input alternating current. Time is taken on x-axis. Voltage values are taken on y-axis. Then AC waveform. This is the AC waveform, alternating current waveform. So here the voltage of AC waveform, positive half cycle voltage is plus V, and negative half cycle voltage is minus V. These are positive half cycles and these are the negative half cycles. So this is taken as the output waveform, output DC that we have to obtain by using this device. So here for all positive input half cycles, the two alternating current cycles, diode D will be in forward biased condition. Means when positive half cycle reaches to secondary coil from the primary, then one of the terminal of the secondary coil, say A, behaves as positive. We know that this acts as positive, means it is the P type and is the N type semiconductor. So PN junction diode, this part acts as positive, so this acts as negative. So for positive half cycles, for all positive half cycles, then diode will be in forward bias, then it conducts current, that current flows through the load, then potential drops across the load. That potential is obtained as output DC. Now for all negative input AC cycles, diode D will be in reverse bias condition because A acts as negative whereas this is P type semiconductor, so it will be in reverse bias condition. Then it doesn't conduct current, no current flows to the load, no potential drops across the load, that's why no rectification. Like next again positive, next negative, positive, negative half cycles, then it rectifies only positive half cycles, no rectification for the negative, then we'll get output waveform like this. That means all positive half cycles only rectified into DC. So like this, half wave rectifier will be worked now. Now its efficiency. Efficiency of half wave rectifier, symbol of the efficiency is eta. The ratio of output DC power to the input AC power is called efficiency of half wave rectifier. The formula is output DC power by input AC power is the formula for efficiency of half wave rectifier. It can be also written as 0.406 into RL by RL plus RF is the exact formula for the efficiency of half wave rectifier, where RL is the load resistance, means output resistance, small RF is the forward resistance of the diode. Now the maximum efficiency of the half wave rectifier, maximum efficiency of the half wave rectifier is eta is equals to 40.6%. Generally it is for ideal diode. For ideal diode, RF value is 0. Then if you write RF 0 here, RL cancel out. Generally efficiency always represented in terms of percentages. That's why you have to multiply it with 100. Then you will get 40.6%. Like that, we can explain about the rectification process and the working of half wave rectifier with a suitable neat diagram.